Hello, everybody, and welcome to video number 3 of our exploration into the polar graphing system. We've had 2 pretty long videos so far, so I'm going to try to make this one a lot shorter. This one's going to cover our last main objective is testing polar coordinates for symmetry. And I said polar coordinates, it really shouldn't be coordinates, it should be equations. So we're going to test our polar equations for symmetry. Now, as I have students take a look at what all these different shapes look like and how to graph them, one of the things I emphasize is, well, cosine gives us symmetry over a polar axis here, where sine gives us symmetry over our theta equals pi over 2 axis. I didn't graph these on the last notes because we were running a little bit long on time, but if you remember, our graph actually looked like this. The petals are a little bit fatter than what I'm actually graphing here. That one looks a little bit better, but this symmetry occurs because of sine or cosine. Now, what's happening algebraically, if we want to take a look at this, I want to kind of tie it back to what we did with rectangular, where if we had symmetry with the x-axis, we replace negative y with y. Where if we have symmetry with the polar axis, we're going to replace negative theta with theta. And the reason for that is because if we have negative theta here, which gives us the exact same value as positive theta, and everybody, just so you know, I'm looking in the rectangular system at this point. If these are the same, then I have my polar axis symmetry, which is exactly why cosine of theta is giving us that polar axis symmetry. So let's actually look at A. A does not have a cosine in there, so I'm not expecting us to have polar axis symmetry. I am expecting the polar axis symmetry to occur right here, though, and that's because of the cosine. So what I have students do is I have them identify what symmetry is going to occur and then prove that symmetry. I can show why this doesn't work. Like if I have r equals 1 minus sine of negative theta, that is 1 minus, if you remember, sine is an odd function, so we can take that negative out. 1 minus negative sine of theta, and that's due to the fact that this is odd again. So that gives us the equation 1 plus sine theta. Well, 1 plus sine of theta is not the exact same equation as what we have up here. So therefore, there is no polar axis. So this is a proof of why we have no polar axis symmetry. Now, we should have our polar axis symmetry here, and that's because if I replace my theta with negative theta, remember cosine is even, so cosine of negative theta is equivalent to the cosine of theta, and voila, we have the exact same equation, so we have our polar axis symmetry. Now, what happens here? Do we have polar axis symmetry or not? R squared is 4 sine 2 theta, so do we have our polar axis? R squared is 4 sine of 2 times negative theta. And just like before, that now is equivalent to negative 4 sine of 2 theta. So R squared is negative 4 sine 2 theta, not the same thing, so no polar axis symmetry. The second one is theta equals pi over 2 symmetry. So our theta equals pi over 2 symmetry, and actually, before I get into that, there is something that I do want to emphasize, that if not, we actually have what we call an inconclusive test. Unfortunately, because I know what these graphs look like, I jumped the gun and said, hey, that doesn't have the symmetry. What this actually tells us is this is inconclusive. And we have to come up with another test to show why that actually works. If we were in class, I'd go into a much deeper exploration of this than what I'm going to do here. So I really should have said over here inconclusive as well. All right, let's jump into the second type of symmetry. So here I did my polar axis symmetry. Let me change colors. Now we're going to look at theta equals pi over 2 symmetry. Now to do that, we're going to replace pi minus theta for theta. And just as kind of like a visual of why that would happen is because if you remember sine of theta, if this is our theta right here, sine, which shows this y-axis symmetry, If we take pi minus theta, we get the exact same y value, which is what's going to cause that theta equals pi over 2 symmetry. So let's actually show that. It should occur here, and we're going to prove it. Now, the way that we are going to prove it is we have to do the difference of angles when it comes to sine. So this is 1 minus, and if you remember way back to chapter 7, sine theta, or sine pi cosine theta minus cosine theta cosine pi sine theta. So 1 minus the sine of pi is 0, and then the cosine of pi is -1. So what actually happens is this ends up being 1, the double negatives occurring right here. Cause that to be a plus. Actually, that's a triple negative. That triple negative causes it to still be minus. So voila, we have the theta equals pi over 2 symmetry as a result. For part B, I'm not expecting this to happen. That's because of the cosine. Because I'm not expecting this to happen, let's put a check here. Let's see why it doesn't work. So r equals 1 plus 2 cosine pi minus theta. So if you remember the sum formula for cosine, I guess the difference formula, cosine pi, cosine theta ends up being plus, cosine is that opposite, sine pi, sine theta. That's 1 plus 2 times -1 times cosine theta, and then plus 0 times sine theta. So this gives us 1 minus 2 cosine theta. It's a different equation, therefore this is an inconclusive test. Now it actually does not have that symmetry, but at the same time, this is more of using algebra to verify whether it does or not. Now on this one, are we expecting the symmetry to occur or not, and why? So let's take a look at r squared is 4 sine of 2 times pi minus theta. So that's now 4 sine of 2 pi minus 2 theta. And we can go ahead and keep working through our tests. So this is 4 times sine 2 pi cosine 2 theta minus, because sine keeps its signs, cosine 2 pi cosine 2 theta. So that's 4 times sine of 2 pi is 0. And cosine of 2 pi is 1. So this is 4 times negative cosine of 2 theta. Negative cosine of 2 theta, which gives me -4 cosine of 2 theta. So what this tells me is we don't have any symmetry. Let's actually verify that on our graph. If we verify that on our graph, we're going to have to do this as 2 sine of, let me keep this in here. So this will be 2 times, I guess we can leave it as a square root of 4 sine of 2x. And if we look at our graph here, we don't actually have that symmetry, and that's because of the imaginary pedals that I talked about with the last video. So we don't have the symmetry, and that test actually showed this was inconclusive. It really doesn't have the symmetry, but our test shows a lot of that inconclusive means it doesn't actually happen. Our third test is pole symmetry. So when we have pole symmetry, what we do, we actually have 2 different tests for this. With the pole symmetry, we will test to see whatever our theta is. If we add pi onto that, we should end up with the same angle, which represents that pole symmetry. Or the other test that we have is whatever occurs with the positive radius. If we occur with a negative radius, then we get the exact same thing. So we have 2 distinct tests that we use for this, and a lot of that's going to be based off of which form that we're in. So for instance, on A, if I replace my r with negative r, it's pretty clear that that doesn't give us the same equation. Therefore, we're not going to use that negative r test on that graph. But what about the other one? So r equals 1 minus sine of theta plus pi. Now everybody, what shape is this? This is a cardioid. And would a cardioid actually have that symmetry? No, it does not. Because a cardioid wouldn't have the symmetry over the pole. Therefore, this one shouldn't work as well. So typically in class, what I say is these are our algebra ways of verifying whether the test actually, or whether the graph has a symmetry or not. I usually say what symmetry is there and prove it using the test, because these tests are different, that these tests don't have, or don't tell us if they don't have the symmetry. They actually just tell us if it's inconclusive or not. So what I typically have students do is prove whatever symmetry results. That way it's not just like a lot of wasted time. Like this, I would say is wasted because I'm not actually, I know it doesn't have the symmetry. I know this is a cardioid. Because a cardioid does not have pole symmetry, this isn't going to work. And I've been saying the same thing over and over again. Let's actually just do it. So 1 minus sine theta cosine pi, and then plus cosine theta sine pi. So 1 minus cosine of pi is -1, so negative sine theta, and then sine pi is 0, so I get 1 plus sine theta, which is not the same thing as what I started with. So this is officially inconclusive, but we know that it doesn't actually have that symmetry. Now this one, 1 plus cosine theta. 1 plus cosine theta, what shape is, or 2 cosine theta, what shape is this? This is a limacon. Now, does this limacon have a loop or no? A is smaller than B. And why I care about that is my largest radius is 1 plus 2. My smallest radius is 1 minus 2. The fact that I have a negative radius means that there is a loop, so with a loop. Does a limacon with a loop, and it's cosine, so it's going to be something similar to that one. Does this limacon with a loop have pole symmetry? No. And when I say pole symmetry, what would have pole symmetry? Pretty much a lot of these roses are going to have pole symmetry. So this one right here has pole symmetry. This rose right here has pole symmetry because what you see in one quadrant is the same as what you see in the other quadrant. So this one does not have it. So let's actually prove that, or let's show that this test is inconclusive. 2 cosine of theta plus pi. Now, once again, if I make this radius negative instead of positive, that's where I'm going to rule out that test. So let's test the other one. So that's 1 plus 2 cosine theta cosine pi minus sine theta sine pi. I know it seems ridiculous that we're going through this, but at the same time, sometimes it's important to prove that we don't know things, that we don't know what's going to occur. So that's negative cosine theta because -1 minus 0, so 1 minus 2 cosine theta. So once again, we have an inconclusive test because it's not equivalent to what we started with. Now on this one, we could also do that r squared is 4 sine of 2 times theta plus pi. We could do this, but I'm going to say that's not an efficient use of time because we know that if we replace the r with a negative r, we are going to get the exact same equation. So please be smart about what test you're using in order to prove your symmetry. So this one does have pole symmetry. And why does it have pole symmetry? Because this one is a r squared equals, this one is a lemniscate. So knowing what equation gives you what graph is very, very helpful when it comes to actually verifying what symmetry is going to occur. So hopefully you guys found this beneficial so we could see a lot of information about graphing in the polar axis. Again, if we were in the classroom, we'd be going into this in a lot more depth. Sadly, we're not able to, but that's okay because remember, you've got your back. And I said that backwards. I've got your back and you've got your back. Take care and signing off.